Okay, okay. So, a very good morning to one and all present here. And Professor Sneha Singha, on behalf of the School of Computing, welcome you all to this been organized on data structures for our students. So, to deliver this talk, Aman sir, can you please mute? Okay. So to deliver this talk, we have with us here our expert speaker, Mr. Sandeep Patil. He's a firmware development engineer at Intel India Private Limited, Bangalore. Sir has over 7 years of experience with expertise in UEFI, ACPI architecture, and C language-based firmwares like UEFI, RTOs like ThreadX, Zephyr, Free RTOs. And also, Sir is passionate about learning new domains. Sir has under his hats many projects like sign language processing, investigation of robots formation. And at a very young age, Sir has also received many recognitions at Intel's and many awards in his career as well. So it is indeed an honor to have you here, Sir. And we really look forward for the interesting session, and we really look forward to having share your expertise also with us. So over to you, sir. You may please take over the session.
Sure. Thank you for such warm words, and thanks for having me. Everyone can start video. It's like for me looking at screen and delivering. So if somebody can join over video, should be fine. Or we can start. Okay.
Yes, sir. We can start. Yes.
Yeah. We'll talk about importance of data structures and algorithm. Why those are important in our computer science. So I hope my screen is visible to you.
Yes, sir.
Okay. So this is the agenda that we will be covering today. What is data structures? It's just for the communication starter, and how we can compare data structures and algorithm with real world stuff, and how important data structure is in our real life, and why do you need to learn data structures, and how are we using in industry these data structures and algorithms. Yeah. So this is overall agenda that we'll cover today. So let's start one by one. So the first question that we get is, what is data structure and algorithm? Anyways, you guys are second year students and overall, right? So you must be knowing, but let's make some sense out of those words, like data structures. So before that, we know what is computer is, right? Computer is nothing but a computing device. What does it compute? It computes data, and whatever data, or you can say it's a data manipulating device, right? So every time we play around data, so whatever kind of data is there, we are going to feed it to computer, and we are going to make sense out of it, and we are going to get the information out of it. So computer is nothing but the one which gathers data and gives the information out of it, right? So it's all around data that computer works on. So see, the foundation is data, right? So how this data is represented, how this data is stored or retrieved will play a major role in computer's life, right? Or in our life. So the way we store our data is nothing but the data structure, right? And the way we retrieve it. So that is structure and data. Data stored in form of some structure is nothing but data structure. Yeah. So and feel free to interrupt me in between if you have any question, or you can have some chats. Uh, okay. So that is nothing but data structures, and like the way we store and retrieve the data, and how overall we are going to optimize the data is nothing but we are going to use the algorithm. It's the set of instructions that we are going to operate on data structures is nothing but the algorithm, right? Okay, so how we can compare this data structure to real world stuff? So this image is taken from internet. Okay, so uh, you don't have to bother about these uh, names. So you can see these images, like these are very big buildings, and it has some base, right? And the way the building is designed, on based on that, its base is designed. So even if you see this second image, second building, you can see how that its base is defined. It's uniform, or if you see at first image, it's not uniform, or there is some difference. So the way you're going to have your applications or upper layers, based on that, you're going to design your data structures. So data structure can vary, has to vary based on your applications, right? That's why we have multiple types of data structures. So here, if you see, every building or every infrastructure that we have is based on some basics or some base. Even we have these homes or roads, right? All those have some base that we don't see, but you can see its outcome, like the upper land portion, right? Simply, if you see the second image, that base is almost 45 meters in deep, right? So that's that much base it requires, and that much solid base it needed just to make this tall building. So the way building or infrastructure is designed, in our real life, we need data structure as a base for our softwares, right? So it's something you can relate to the base, so or basics that we need to have. Based on that only, we are going to develop anything that we want. Okay, so how important data structures in our regular life, right? Computer science life. We usually what we expect from computer, right? Speed, then precision, and amount of size that that particular program is going to take, right? So in our real world also, these three factors are going to play a role in some sense. Like precision, like we have autonomous cars, that those cars has to be very precise, right? You don't bother about its size or anything, but it has to be very accurate and precise. So all these aspects are always related to the data structures. For example, we have this display resolution. For example, we have monitors and display. So you can see here we have 4K monitors. So simply to represent one screen or one frame of monitor, we need these many 82 million pixels per frame, right? And if you want to, so it nothing's but 82 million pixel and every pixel we represent how, using 32-bit words into four words, right? Red, green, blue, and the transparency. So we have four data words of 32 bits wide. So if you have to represent one image, then it is going to take almost 126 MB. That sort of data it is going to take over our screen. So for example, whatever screen that you are seeing right now, so if it is 4K, then it is going to take 126 MB per frame to manipulate or to represent it, right? And we have these very high end videos, or we have these high end graphical games, right? And those we play at 60 fps, in the sense 60 frames per second. So you can assume 126 MB of data per second, like in 1 second we have 60 frames, so it is going to be 7.3 gbps of data. So how that's, but you can see the data that we are presenting here, it's 7.3 GB, right? But if you see right now you are processing, or you are able to see my screen, it is not going to take 7.3 gbps, or accordingly probably 1 gbps. It's not going to take. Why? So the way the data is optimized, the way data is represented or manipulated is going to play a really big role. So for example, if you want to create 2 hours movie with this sort of if I simply dump the raw data for every screen or every frame that we have, then it is going to create one picture of one lot of TVs. uh, are we are we going to operate on such huge amount of data? How much time it will take, right? So that is where our data structures and algorithms will play come into picture, and the way we optimize that data, it's always based on data structures. Okay, so you can see how much data that it can create simply uh, by one slice or by 1 second. So I hope in this resolution it gives that importance of data structures, or how the manipulation of data has to be done accurately or correctly or precisely, right? Or let's take a satellite launch. uh, so we have this launches, right? Recently we had that another launch. So how precise that data is, so every calculation that we are going to that they are going to do, okay, that has to be very precise. For example, uh, uh, if if they have some uh, operation like 1.7 or those floating points operations, right? And if they seal it till the second digit, and they remove the remaining digits, is it is going to play really big role in their life, because probably because of that particular ceiling or uh, floor, because of that floor and ceiling, in the sense removing the extra uh, digits after dot is going to create huge amount of impact on there. Probably the rocket might tilt somewhere or something like that. So the way, whether we are using float and long, or uh, bigger floats, right? 32-bit, 64-bit. These are all going to play a big role in even the satellite launch. We have GPS system. We always wonder, like whenever we go to any direction, uh, GPS shows good amount of correct data. Now I see Navic, whatever that we have, Indian satellites. All those gives good accuracy, right? In like 1 pixel is nothing but less than 1 meter of your land, 1 meter square of land. So how much they are, like 400 kilometers or around that range height, and they're still giving us the precision data, precise data. So that has to be calculated in very in good precision format. So simply if I consider 32-bit number, is it going to be sufficient? No. So you need some good data structures. Probably it is primitive or non-primitive. For example, in this case, the if I'm going to capture only my area, and I'm going to install the GPS only for my area, probably I need 32 bits of float. That probably is sufficient. But if you are going to create all this stuff for whole world or whole earth, right, we need big amount of data structures. So so that is how even the data structures can be used in that. Then the autonomous car. So we are getting these autonomous cars. Even in our new cars we have this uh, forget I forgot that name. So we have these autonomous features, right? Even in so like when you go over the highways, you can give the control to the car, something like that. Those features are there in car. And if while driving that particular car, it creates enormous amount of data. Like it has leader sensor, which is 3d 3D sensors and image sensors, infrared sensors. It will have a lot of sensors, right? And and those sensors are from all the dimensions, from all the sides, almost 360 sides, right? 360-degree. So all this data has to be manipulated and has to be taken precisely. And based on that, how quickly you're going to manipulate the data is going to play a role. Okay. So, for example, let's assume this autonomous car is going over my way, and it has got the data. It has got the indicator that okay, I am in front of that car. It has to take this uh, action at the same seconds, less than a second, but it has GBs of data, right? Then how it is going to process that GBs of data in less than millisecond, or in a milliseconds. So you can either optimize, you can have high performance CPUs, high performance GPUs, or whatever. So you can have it. But if you you have all these hardware features, but if you still don't use that hardware features efficiently, then it is going to play uh, very bad, right? So you need to create the software on top of the hardware that we have received, and that software has to be very efficient. Until your software is not efficient, your hardware is not going to be as that useful. So software is going to play, and software in the sense data structures and your algorithms is going to play a big role. So in all these aspects, there will be hell amount of examples to just represent how much data that we gather. For example, even the autonomous cars that we have, it gathers like for a single day, according to some surveys, it creates TBs of data per day. Okay, and it even based on that, it itself heals, or itself optimizes, like artificial intelligence. Okay, and all that data has to be again manipulated. And if you consider there will be lakhs of cars, and all that data has to be it stores whole web data. Right now, does it store? Probably not. It has optimized it. Uh, it has created algorithms based on it, and it has optimized a big at very great extent that you get your answers immediately, no matter what you ask. So all that data you're going to store, and then only you're going to retrieve. So again, data structures will come into picture. Then autonomous automation industry. So every time anything we got, for example, this computer, or any car or anything that is built today, all these industries, most of the part of those industries, it is automated. For example, your car coloring is done, so that is also automated. So if while that is automated, and if because of some glitch there is some uh, the color mismatch at some pixels or at some part of the body, are you going to accept it? No. So that sort of fault, uh, I mean, avoider software that you need to have. So algorithms, it will try to always detect, it will try to always check whether there are any hardware errors or not every milliseconds or so. And it is based on that, based on all those data, based on lot of data that it is going to get through sensors, it will always make itself aware, right, whether to color that car or not, with that color or not. So all these factors are going to get impacted again by data structures. Okay, so we might wonder how uh, okay, so let's go anyways. Does anyone has any question over there? Feel free to ask. Students, I'm not a teacher, so uh, so you can be, I'm like you only, it's like student, so you can go ahead and ask any question. Okay, so the next point, uh, do you really need to learn data structures and algorithm or not? So let's assume you're someone not from engineering background. Okay, and I'm going to tell you that you have to create one Android application. Okay, what actions you're going to take? You'll try to learn from Google. You'll try to and based on that, definitely you're going to create application. Okay, no matter whether you're from engineering background or you're from non-engineering background, over the time, once you learn something, you're going to create that application. Okay, but the way that you're going to create the application and how cleanly you're going to create that application, that will matter, right? For example, we have this WhatsApp, right? The way we scroll that application, that smoothness, that for example, WhatsApp. Okay, I'm not promoting WhatsApp. uh, so that smoothness sort of user interface we need, right? So all that will play a big role. So you're from non-engineering background, and you are not much aware at initial stage about this design patterns or data structures, right? Then you will end up creating application, but that application is going to take, whether it will have load time, whether it will have whenever user experience, UX, user experience will not be that great. So how you're going to have, how you're going to distinguish yourself as a computer engineering student with others, right? Then you need to have your basics clear, or your base has to be very clear. So how that is going to get cleared? So if that is through practice, right? And what practice you need to do is what we need to focus. So these data structures and algorithms is something that I believe that at student life, that is what will matter, where how frequently or how good you do that practice of data structures and algorithm, that is going to play the role, and that is going to distinguish yourself with others. Okay. uh, with respect to knowledge. So, and based on that knowledge only, you're going to write some application, you're going to design new systems that you will design over the time, right? And how, and that is all analytical skills. So once you uh, uh, start practicing this DSA, then only your analytical skill will be improved. And even I believe in that perspective that if your analytical skill via data structure, whatever is going to get improved, that will help you in your real life as well. So you'll even take the mature decisions in a lot of aspects just because your analytical skills are improved. Okay. So data structures is simply, if uh, I'm assuming you're practicing it really good. Okay. Based on that, it is going to create much more difference in your real life as well. So for example, okay, we have that. So again, then we have the second point is design patterns. So we have these homes constructed, right? And we always hear that, okay, the hall has to be at this side or something like that. So we always get all that information, or engineer do give us that information based on some information, right? And it has some base, and that is nothing but the experience that they have gained, and based on that only they have created some design patterns for our home. So if you see the amount of experience that is invested to have such good efficient uh, homes, is because of the analytical skill that they got, right? And the way that is getting defined is nothing but design pattern. So all those design patterns will you will eventually learn those design patterns in your career life, and those design patterns will make sense where if you have data structures and algorithms, uh, good control over that. Okay. So even the yeah, so that is it. Then approach to solve the problem. So I remember one of the cryptography related one algorithm, that public key cryptography by Whitfield. I remember because I saw that guy once in Pune in one lecture. Uh, so uh, so that algorithm, if you see, it's in short, I'll tell you the algorithm that I want to share some data. Probably this is also encrypted. Okay, whatever communication that we are having. I saw the so I want to transfer the data, and I want it to be secured, right? And the security has to be like, uh, I will lock it and you will unlock it. Only you will unlock it, or you will lock it. I will only unlock it. So there has to be some secure mechanism. Okay, and to create that secure mechanism, we'll first exchange our keys. The key, even you don't know my key and I don't know your key, so still the data has to be encrypted. That's the basic task. A whole web is defined based on that right now. And so now I'm going to exchange the data. So now this key is based on some raw data, and that data is nothing but prime numbers. There is one prime number pair, that this prime number pair is going to be paired with only this prime number. So he has to find out what's the prime number has to be. Prime number pair has to be. That's all the algorithm is. So if you see whenever you're going to implement that algorithm, you will see it, you have implemented it very less time, but the process that he must have gone through must be really great, right? Like uh, you will end up thinking that it makes sense, this algorithm makes sense, and it is not so complex. It is just because the analytical skill, uh, it is not because he has learned data structures or something. It's about analytical skill, right? The way his mathematician experts or someone. So all that sort of analytical skill based related to the computer science, you're going to get through these basics. So okay, I'm not claiming here only data structures and algorithm is going to give you that analytical skills. Okay, there will be hell amount of syllabus will have. Okay, then you have a lot of all these data structures like preemptive, primitive, or non-primitive, int, long, or there are a lot of right arrays, queues, trees. And are you going to use those data structures? Usually we get that question whether probably we may not be, or we might have heard at a lot of extent that we learn all these aspects in our computer life or in our engineering life, but we don't use it in industry. That's not the reality. Okay, I just wanted to clear that whatever you are learning right now, it is going to be used. It is going to create you a good engineer. You become a good engineer. You will become a good engineer based on that career only, curriculum only. Okay, so try to focus on that. So, but are you going to use whatever you are studying right now as is? No, it, but it's much required basics, right? On top of that only you're going to build something. So for example, you might have that microprocessor 8086 or 8051 coding. Okay, so are you going to use the same coding in the industry life? No, but there will be some different CPUs or microcontrollers or anything, different systems, right? But to know that system, you need to know the basic systems, how those systems have evolved. So that part of knowledge you will gather, and that will be helpful in long run in your career. So so yeah, in some sense, in lot of sense, I mean, it will be useful whatever you're studying right now. Okay, so again, while studying data structures, you will come across a lot of complex data structures, graph theories, and AVL trees. There is red black trees, a lot of stuff, right? Then we get again one question that are we really using graph trees or in general data structures in our work right now? Then yes, consciously and unconsciously, yes. Like for example, I'll go through these examples, but this is one of the link that you can also go through. This is the code that we actually work on in industry. And let me open this link. So if you see here, this is the base package that is being created. Okay, and you will see there are a lot of stuff in here. Here quick sort, you can see linked list. uh, so all this, there will be a lot of strings, uh, stack. So you can see everything is really in use right now. Okay, even it's a pure C code. You can go ahead and download all this information. You can see it's okay, part of the code you're going to write in your curriculum also, like the way you're going to write the stack. Probably there will be some different way. There will be something extra, some extra parameters will be there. Okay, then so those sort of extra modifications will be there, but that is based on your knowledge that you know the stack. Okay, so you can go through this link. I can provide you later in chat. Okay, so in firmware, definitely we are using these graphs, trees, queues, sort. A lot of our algorithms that we have, or DS that we have, we use it. Okay, so for example, I can tell you in firmware, like key press event, we have this keyboard, and whenever we press any key, uh, at the same time, and if you start typing fast, still you will get the whatever the first key press, you should get that first printed or executed, right? So that is sort of queue, right? And those queues are implemented in our hardware or in software, so that you get whatever keystrokes that you have faced. No matter, sometimes you will feel that okay, this is hung, this application is hung, but still you start typing it. Still you get, once that restores, program is restored, you get that uh, all those characters printed in your screen, right? You might have encountered such experiences, and uh, so you can see here. So unless and until the data is not consumed, the queue is not restored. The queue is not flushed, right? So so this is one of the basic example of queue that we are using. So for example, here this system work, and we have multiple IO modules, memory boards, and CPU. So we have this IO module. For example, it's a keyboard. It is going to execute queue, or we in the this SoC or CPU will have its, probably will have its corresponding somewhere, right? Or it might be implemented from in firmware. Okay, so it is the basic building block that the current system that we have. So yes, we do use it. Again, the interrupts, interrupts, whatever, uh, when we press any key, it's an interrupt. When we power source your machine, it's an interrupt, right? Interrupt is someone who interrupt your system. So, or okay, okay, so all these sort of interrupts you get, even when you get any network package and you want that data, all every time you get anything, any screen, or you get anything from different hardware, is nothing but an interrupt. Then those interrupts are has to be prioritized, or those will be queued. All those decisions are based on whether you will learn the priority queue and you'll learn the queue. All those informations or all those algorithms, data structures have been clubbed together, and based on that you will create the priority queues, normal queues, and a lot of stuff on top of it, right? Whether again you will come across the priority inversion, whether you gave the priority to some bigger task, and the task is taking hell amount of time, then again you need to give the uh, timing to time to another task. So all these aspects are created based on your queues. Then you will add some stacks or whatever. So it's always the clubbing of all the basics data structures that we have. Then data transfers, yeah. Then the code compilation and runtime. Okay, so again, we every time we run any code, we first compile it, and even that compilation phase is based on the queues and stacks that we have. So let's see that example in next slides. Let's see the code runtime. When we run any code, right? So this is the image. It's a for example image. Okay, uh, so taken from internet. You can also take this image. It's very good example to showcase. Uh, so you can see here the program is, you have created the program is in RAM now, right? Now you're going to execute it. Now how your functions, you will create some recursive functions, or you will create some functions. Those functions are going to be stacked, right? If this function is executed, now this function is calling another function. Okay, now that function is calling another function. So all that execution steps or has to be stored in some way. Like the latest function that is being called has to be executed first, right? So and who called it should be executed later, and likewise. So here also it's a stack. Okay, and based on stack only we are executing the functions. So whatever whatever been uh, we have learned is is executed or is being used in our computer sorry, in our curriculum life as well. So you can see the stack is growing from this side, the heap is growing from another side. So probably they might collide at some time, right? If you might have done those experiments in C language, where you call a function recursively and you call it without any condition, and at the end you will get to know the error, that stack overflow error that you will get, right? And those stack overflow errors are nothing but this. Okay, the stack is filling, and it reached to the heap. heap, uh, the top of heap, right? And when this two collides to the each other, you get that error, right? Do I mean better you try that experiment. It's a good experiment to know this, how even this stack is being used in your regular program as well. No matter whatever program it is, probably even your Java programs probably can, I don't know, but C++ programs will definitely give you that perspective. So you can see even in code runtime also we are using all these aspects. So even if you see, we always use this Google Map for our trip planning. So while doing that, we just place some map points on map, and once you place it, it can tell you how much distance it is, and even based on that, we check which route will be better for me. For example, I'm in Pune. I want to go to Mahabaleshwar. I want to go to Mumbai, and I want to go to Raigad. Okay, there is this triangle, or and apart from that, I want to go to some uh, Solapur. Okay, so that it has created some irregular map. Okay, so now I want to start it from Pune. How I'm going to start it? So it is always in our unconsciously we try to use the computer science there. Okay, the way the Dijkstra's algorithm works or something, we actually in our unconscious mind we use those algorithms and we play around it, right? So while you plan it, probably you will go to Solapur first, then Mumbai or something. So that is based on the data that you have, the distance, the speed. Based on the distance or the speed, everything, every aspect you will calculate, right? And based on that only you're going to plan your trip. Okay. So all this is nothing but your data structures that you have, graphs and trees that you are using, right? That is also while driving the same scenario. Okay, so when I drive, for example, I have so earlier trip planning that you were doing, that was again based on those distances. Again, you can have the driving experiences like if I want to reach from distance A to distance B. Okay, and there are two routes, and one route is shorter and in the distance, and another route is longer, but that longer route is taking very less time, and the shorter route is taking very much time compared to this one, because the road is not good or it has a lot of bumps or anything. And based on that we take those decisions, right? In that aspect, then your priority will come into picture, whether you want, how you want to go through, right? uh, for example, if I have considered the longer route, uh, then my priority is based on the speed that I have. Okay, these factors will always play bigger role with what you need, whether you want to store data or whether you want to optimize data but slower speed, and optimized speed, but the data it is going to take, like in this case fuel, it is going to take much more. So sort of, so these factors even in our real life we play along, right? So yeah, yeah. So that is all in this. Does anybody has any question? You can raise your hand. And I hope I'm very clear. Okay. So DSA in overall computer science. Uh, DSA, how do we use in overall computer design? The process scheduler we have. The scheduler is nothing but it's the combination of stacks and queues, everything, right? Priorities. That process scheduler, uh, even the way probably we have this screen, but we have resumed it and we have opened something else. So all this scheduling is best, right? It is done by process scheduler. So in that process scheduler also, whatever algorithms that we are going is going to play a bigger role. uh, for example, let's assume uh, the very precise algorithms, right? Or the priorities. Example, which process you need to schedule that will have some priority. For example, we have some uh, autonomous cars. uh, Skip it. We have satellite, right? And satellite, GPS satellite, and GPS satellite has to give the data to you, or there is some issue with the satellite where it has got hidden up, right? So its temperature sensors will give its interrupts. Okay. And that you have to shut it down. So now there are two interrupts, whether you need to give the data to the consumer, or whether I need to switch myself off. Which decision I need to take. Though all those sort of decisions will be based on will the priority that is assigned to your task, right? Which is the highest priority task. Or similarly, in interrupts as well, in computer science, we'll have maskable interrupt, unmaskable, or all those sort of interrupts, right? And here you will take eventually you will take the priority. You will give the priority to the temperature sensor task, right? So you gave that priority, and once you gave that priority, it has to execute its task very immediately. It has to shut it down, that system, effectively, immediately, right? And all those actions will be taken in milliseconds. Okay. So for example, I'll tell you one example where we had experienced such issues. Uh, for example, we had this autonomous car, and we in our one of our project we wanted to uh, check the health of our car immediately. Every millisecond or every 10 milliseconds, we wanted to check the health of our car. Okay. And if the health of the car is not right at that 10th milliseconds, then we are going to turn that car to the safe position. And we were getting the issues where 10 milliseconds, because of rather than 10 milliseconds, it was taking 20 milliseconds for us to execute that particular task. Okay. So that 20 millisecond, because of that just 10 milliseconds extra overhead, our car was going into safe condition, safe state. Or if we were sending the acknowledgement to the actual the controller, car controller, that okay, you need to stop now. But the decision was taken at 10th milliseconds extra time, right? That 10 millisecond plays really big time, big uh, uh, role in even in all these scenarios. So we had to optimize our algorithms, we had to optimize our data structures. For example, the way even simply we were copying like 10 bytes of data, and those 10 bytes of data we were just doing two copies. Okay. We avoided that, we created only one copies, and just because 10 bytes of data copying only one time optimized our times at greater extent. So if you see, when the time is critical, very critical, even your bytes are going to play a bigger role. Okay. Then the program execution. Yeah, we have covered that. RAM design. We have this everything that we execute is always we take it into the RAM, right? Every program that we have. And now why it is called RAM, random access memory? It's just because it's random access memory. So whenever you are trying to access anything from RAM, okay, that has to be at same time. So there is one data block at location 1 and at location end, at the end. Okay. If the CPU wants to access this data and CPU wants to access this data, both data has to be accessed at the same time. Okay. So if you see, there is some time crunch, there is some time necessity that everything has to be mapped. hashed sort of, right? That the time has to be the same. Okay, so in this RAM design, what's the hardware design in this? That we have this hashed map. The way the hash map is in RAM is being used is in hardware design. The hash mapping is done in hardware design for RAM. So every signal has to be done through these, unless until we get to know these hash maps, how those works. We will not be able to manipulate that, or we will not be able to create that analytics, right? uh, to have that RAM design. So that sort of problems, or we use DSA in our computer. Then artificial intelligence. So we'll take one example of artificial intelligence in next slides. Uh, Today everything is artificial intelligence, right? And based on those, okay, we'll take then the memory management. The memory management unit that we have, right? And that how that efficient has to be. You can see simply by using this example. Memory management unit, what it does, it allocates memory to some processor and it deallocates memory from that processor. Now, how that is the task of memory management, and how your program is going to manage the memory that it needs. Also it is going to play a role, like the example that I gave you from that autonomous car, where 10 milliseconds, simply 1 byte was, or 10 bytes was playing that sort of role. So if you see here, structure 1 and structure 2, right? Structure 1 is defined like this: byte b1 interrupt I1 num, and then byte b2 num, and struct 2 is byte byte int. So if you see, this byte is there, and after that int is there, and then the byte is there. So if you see, the struct1 is going to be stored like this: b1 num, I1 num, and b2 num. It is going to take like 3 words of memory. But how much we were expecting? 1 byte, 32, 4 bytes plus 1 byte, 6 bytes, right? That is what we were expecting, but it has to be closer to that. But in this, the way that this structure is defined, just because the way this is defined, it is taking 3 words, like 12 bytes of memory. If you see the structure too, byte is defined, and then int is defined. In this case, byte b1 will be stored here, byte b2 will be stored here, and I1 will be stored at next word. Everything is aligned, okay? uh, Word aligned or byte aligned. So it's word aligned always in this scenario. So if you see here, byte 1 is stored here and b2 is stored here. So how much memory it has taken? These 2 bytes will be the extra ones that we cannot help with, and the I1. So you can see here 8 bytes of memory it has taken. So it directly, just the way we have defined our structures, it played a big role. Like it directly removed 8 bytes of 4 bytes of memory, right? So all these aspects, all these design patterns or design ways will play a bigger role in our life, computer science life, right? So let's assume the DSA in database. So always we learn this data structure, right? And data structures usually we, at least I used to do. So we fix that operating system, and I have one subject of operating system. I have data structures. I have database. All these subjects we usually keep scattered. We don't link it to each other. So if you try to link it, like the way database is designed, that is nothing but underneath it is a C program or something. It is the data structures that it is using, right? So everything is linked and will be consumed together, right? So database are the bigger user of data structures, okay? And everything is about data, as you know. So you can see the WhatsApp, the experience of WhatsApp that you get, or any social media or live feed. So if you open any social media site, okay, So in that, if you open it and it is taking L amount of time, that like it is hanging the web pages, are you going to accept that site? No, right? So it has to be very responsive and it has to give us the accurate data. So all that is needed, and how you're going to implement that is going to play a bigger role. So we used to have, in one of our projects we had one. It was the website for e-commerce, okay, and they had lot of records in data in tables. And whenever we used to go into that particular tab, what was happening, I pressed the tab and the loading icon was coming for like 5 seconds. Do we accept it? No. It was coming just because the way the queries were, we were sending the queries from web pages to the server, and those queries were not good. The way they had done the joins, or the way they were trying to manipulate the data from those tables, it was not that optimized. Simply when we optimized those queries and we cleaned it, we were getting in seconds. So all these queries, how you design those queries is going to play a bigger role, and ultimately that is the data structure, right? So if you see in this particular example, match row, match rows, that is what I expect. So there are two databases, database one and database two circles, and there is some common elements. Now these common elements I can find via multiple ways. I have came up with two ways here, but you can do like fair amount of ways, right? And uh, so I- so if I want common elements, now what I can do, I can take the index or the matching column from this table or database or table, and I'll compare with this one. Individually, I will compare. If I start doing that, it is going to take n square of uh, speed, right? N square of optimization, or n square of time. But if assuming n is the number of elements. But if I sort this database and if I sort this database, and based on that, if I do the binary search, and based on that, if I come up with matched rows, it is going to take n log n sort of time in accord related to that, right? So it is going to play a bigger role the way you query the database, and based on that only you are going to get the great user experience that you expect, right? So yeah, so in database also, whatever data structures that we use ultimately are being used, and those are nothing but your data structures only. So everything is related. So every subject that we have, then the mall items protein. So whenever we go into any mall, we see, right, this is one of the sort of artificial intelligence sort of examples, right, or algorithms that we will be having. So let's take uh, let's take this example where these items are stored near to this rice stuff, right? These are rice packs. I don't endorse any of those. This is just for image. I took this image from Google. I don't own any of this. Okay. So you can see here there are some cosmetics and there are some rice bags. Okay, they have stored it uh, consecutively, right? Then we must wonder why they have kept it near to this item. Like one item is stored always at another item, that is always based on something, right? So how it is done. So let's assume I went to a mall. You all went to mall and you brought something, okay? And you brought something, and based on that data I checked when I took item one, okay? And with that item one, if I took item two, we'll see, using our algorithms, we'll try to find out the probability, and that probability will tell me what, that this whenever this item one is brought, this item two is also brought. What is the probability of that? If I try to find out the probability of all the combinations, the best probability combination, I'll keep it one by one to the other nearby, right? So this is how these small items are groupings are grouped, okay? So this is everything is algorithm. This is everything. This is the real time example that is in use in our malls. Okay. Yeah. So yeah, we can take a lot of examples, but I'll skip those. Okay. Then DSN compiler. So bias code compilation. So if you see or uh, even if you try to compile your Android application, it takes some time, like 10 seconds or something. C code, probably we write shorter codes, and it takes less than a second. But we have GBs of codes, and GBs of codes, it takes hell amount of time. I I remember one story where uh, in early days of our industry, where bias code used to be uh, huge, right? Today it is also huge, but the processing power that we used to have was also limited. But the way the code was written, it we wanted to close everything, right? I mean, we in the sense in general, okay. So and because of that, we never focused on the way the compiler is going to take action on our code, okay. And just because of that, uh, let's assume my job is to build .c files and .h files, create my models, and I'm done, okay. But when I hit the build in the early days, it used to take like 3-4 hours to build the code, okay, because it was a huge code. It is today also a huge code. It's a huge code, and the way the building is done was not that precise. It was, or one of the factor, okay. So so I will hit the build command, we'll try to compile it, and we'll have tea and we'll have sleep, and we'll come back and we'll see whether any errors are there or not. And that's how it used to be, okay. Now so because the way the compilation can be done of the code, okay, so it is going to play a bigger role. So in compiler also we use this, we in the sense we use this today in industry. Everybody, I mean, in every industry, that the way the code is compiled will play a bigger role in your productivity, okay. And the code compilation, that will be the biggest task, and it is, since it is related to your productivity, it has to be quick, right? And if it is not quick, then again today it takes like 4 5 minutes to build some codes, okay. And if I'm sitting for 4 5 minutes, if I'm doing that consecutively activity, and let's assume after 4 minutes I'm getting the error that okay, I missed that semicolon, sort of, we get that from industry, from our uh, college life also, right? Those sort of errors, for compiler errors, if I get it from after like 4 hours after that, then again I'll fix it and I'll run it. So it's a productivity issue, right? And it hampers a lot. So when you optimize it very good, then it is going to get you good outcomes, right? So let's example this, let's take this example. uh, let's take this example. We have file 6. I've created files, 6 files, and this is how the files are linked with each other. Let's assume file 1 is including file 3 and 5, file 2 is including file 3, and file 4 is including 1 and 2. Now this is how the code looks like. Initially this is how the code looks like at the left side. I hope you're following my cursor. And then this is how the code is actually does actually look like. So we have this now, this relationship is built, okay. We have created this dependency matrix, you can say, or dependency expression also, you can say, okay. So here we have all this is how the files are linked. Now what decisions I can take? So if you see here, file 1 is dependent on file 3 and 5. File 1 is dependent on file 3 and 5. These rows you can see. So this is how I have created this tree, okay. uh, uh, Based on the dependency. Now, based on this, what decisions I can take? If I don't use the so you can see here, this is nothing but the graph I have created, and based on that graph, I'm going to feed this graph to the computer, and I'm going to tell them, you compile this first, and this first. Now, what I can do here, I'll compile file 6, I'll compile file 5, I'll compile file 3. Okay, then I'll compile file 2, then file 1. If I have single threaded uh, CPU, okay, single core CPU, this is how I'll do. Okay, then how much time it will take? Let's assume every file is taking 1 seconds. Then 1 2 3 4 5 6 seconds it is going to take to build the final result. uh, okay, and to compile this complete code. Now if I do some extra parallelism, thread 1 I am running this file 3 compilation, thread 2 I am running this, CPU 2 I am running this file 5 compilation, and you can see this is in useless. This is never been referenced. Okay, skip this. Now this file is compiled at one core, one CPU, and this file is compiled at another CPU. Both actions are taken at the same time. How much time it is going to take? 1 second. Okay, and probably if we are going to compile this also, this will be on core 3 or CPU 3. So all these files compilation will be done at second 1 at second 1. So it took 1 second to compile 3 files. Then again the second will be here to compile file 2 and 3. So it will be done at next second. Okay, then once this is done, I'll compile this file, final file. It is going to take 1 second. So if you see, the compilation time has been optimized to 3 seconds almost. So the way that is the way you use your data structures is playing huge role here. So it is just half of the time we have just because we have fixed something, and it has optimized our time at greater extent, right? So these are all lot of examples, and so these are all some examples where we use this uh, data structures, DSAs. Give me 1 minute. Okay, now we have data structures in data processing. The ultimately data structure is processing and manipulation, right? But the way we manipulate this data, whether you're manipulating it via byte by byte or word by word, is also going to play a bigger role. So I just told you this memory copy example, where we wanted to have just 20 milliseconds to 10 milliseconds uh, time. So okay, let's take one more example where I have created one simple copy function. Okay, and in this copy function I'm doing something, and similar stuff, I mean the similar output I'm going to generate in this function as well. What's my task is, I'm going to copy number of bytes. Okay, so these are 3 parameters that I have, and now this function is what this function is doing. This has taken this two uh, arrays, and based on that it has created character pointer, the byte pointer. Okay, and for I to number of bytes, I am copying from source to destination, right? So if you see here, I am doing just the simple copy of source to destination, uh, and this number of bytes. It's just a simple data copy operation, right? And this data copy operation, uh, so that is all the operation is. But I'm doing copy in bytes. Let's take the another example, copy by words. It is also the source, destination, and number of bytes. What I can do, let's assume we have number of bytes equals to 1003. Okay, in this case, uh, if number of bytes equals to 1003, how much time it is going to take? How much IO operation it is going to do? Copy operations, this equals to operation is 1003, right? These many IO operations are going to be done. okay, in this particular IO byte copy by byte operation function. But at the same time, if I write this function where I got these two pointers and number of bytes, and now I have created two different pointers, okay, integer pointers or word pointer, source and destination, and I have I've seen I am dividing those bytes into words and creating the words out of it. And the every 4 bytes I'll copy in one go. So I equals to 0, I is less than number of bytes by 4 because I am copying the data using the word size. In the sense 4 bytes at the one time I'm copying because my word size is 32-bit or 4 bytes. Okay. So this for loop will be executed almost number of 4 bytes, number of bytes divided by 4 times. Okay, so it will be almost 250 times. Okay, this IO operation will be done in this scenario because I have this array of data, right, and it is sequential data, consecutive data, I mean. So I have divided it into words or integers, and I'm copying integer by integer. Here I had copied byte by byte. Now I copied integer by integer, and then since the number is not divisible by 4, it will left 3 bytes. I am copying the remaining 3 bytes using byte by byte. So if you see here, it has taken 250 loops plus 3 loops, right? Yeah, almost 253 loops. So if you see in such simple examples also, how much IO operations we can reduce. The copy by byte took 1003 operations, IO operation, and it took 250 operation. It's like 25% of IO operations right now I'm taking. So if 1 second is what, uh, 1 millisecond, let's assume 1 millisecond is something it is taking for one IO operation, then it is going to take 1 second, 1.3 seconds, right? 1.03, 1.3 seconds of time in this particular function, and this function it will take zero point 0.2 almost milliseconds, right, or 0.2 seconds, 253 seconds. So you can see simply by the way I'm manipulating this data is giving me much more optimization. Okay, so the way you write your data or you process your data or you design your algorithms does play a big role in our daily life. Yeah, yeah. Yeah, so that is all the examples that I have. Yeah, so yeah, okay. So Ari, the final thought I have in general thought that uh, forget about all this technical stuff now, but I always believe that getting educated is your job, right? It's none others. Okay, so yeah, yeah, that is all. Thank you.
Thank you, sir, for guiding us and our students also. Now there is a question answer session. So I request all students if they have any questions, just put your questions in chat box. Am I audible to all of you?
Yes, ma'am, you're audible.
Any questions from students?
So students, you can get comfortable. So let me tell you one story that I remember in my student life. Okay, in my second year when data structures I used to I started learning or computer science in general, right? uh, I used to be very dumb sort of like it was pretty hard for me to understand the data structures, right? And Kondaka ma'am had this policy in our lab that she will teach us the code in the on the blackboard, and once you understand it, then only you will once you understand only, then only you should go to computer and try to write that program. And I used to be a last person who used to sit out from that chair. I used to sit the uh, on the same chair looking at the blackboard to understand it. So it took, sometimes it takes much more time. Even sometimes you will wonder why the hell I am doing that star programs. I don't know whether those are there right now. I, is it there, those stars, and then you print another stars program, and then print another stars program. So we used to have those sort of programs, right? Like prints one star, then two stars, then three stars. It used to take hell amount of time to write such programs in early days, but it was a practical programs. Like it gives you a lot of analytical skills. It will improve your thinking knowledge, and it will help you. So do start practicing all those. I mean, those are really good programs. Yeah.
Okay, sir, thank you so much. Now we are moving towards end of this program. The best and beautiful thing, the best and beautiful things in the world cannot be seen or even touched. They must be felt by her. So thank you is one such a prayed among them. So I consider it a great privilege to propose a vote of thanks to all the dignitaries who have witnessed it as a memorable and successful program. Today my words are not enough to express the gratitude. We have been fortunate to have such a great personality, Sandeep sir, with us. Sir, this is the one of the remarkable, memorable, and knowledgeable guest sessions for our students regarding data structures. With this great session, I am sure that the students must have benefited a lot. Firstly, I am very thankful to you, Sandeep sir, for giving valuable time to us and guiding our students in a wonderful way. Also, I am very thankful to Dr. Rajesh Prasad sir, Associate Dean, MIT School of Computing, Pune, Dr. Rajneesh Kaur Sajdev ma'am, Director, MIT School of Computing, Mr. Ramchandra Pujari sir, Dean, MIT School of Computing, Pune. Without their great support, it's not possible to organize this wonderful session. Also, I would like to thank a special thanks to our beloved today, the Shraddha Kansal Karmani, Dr. Ganesh, for inspiring me to conduct such great session regarding data structure and providing continuous encouragement, guidance, and moral support. I would like to extend thanks to all my faculty members for their kind support with me. Last but not the least, as no program can become successful by a single person, so I extend our big thanks to our wonderful students for their support and showing their interest in this program. In a such a great number of people. So much for this. Once again, thanks everyone. This program is also say have a nice day ahead. Thank you so much. I declare the program is
Thank you for inviting me.